Hey guys, what's up? Eddie Alho here with KissAnalog.com. And today's a very important subject. I'm going to try to not go too long, but basically a conversation about ground. What is ground? There's all kinds of different types of ground, right? There's safety ground, earth ground, chassis ground, floating ground, isolated ground, primary ground, secondary ground, ground planes. I mean, we talk about ground all the time. And what is that? I think it's actually one of the most, arguably, the most confusing terms in electronics. It's just one of these things that everybody in their own field of, specialty or whatever, they use ground. We all have grounds in our schematics and that. But knowing or understanding the bigger picture sometimes I think gets confusing. And so there's some very important aspects about grounding. And one of the things that made me think about this was schematics. I see schematics just drawn in my, view wrong. I mean, wrong symbols, just a four-way intersection, just all kinds of mistakes or things where it just makes me think about the art of electronics. I heard a long time ago, back when I was a young engineer, people were saying the art of electronics is being lost. And I thought, no way, man. We love electronics. We're not going to lose the art of electronics. But as the years have gone by, recent years, I've seen what they were talking about. And anyway, that's a soapbox. But just to help correct that, I think help understand why we use certain ground symbols, I think will go a long ways in helping us understand what ground is and all that kind of stuff. So let's just talk a little bit about it, okay? Let's start off with safety ground. And first of all, let's just talk about AC power. I mean, that's, where you can be killed or injured because of not understanding ground safety. Let's talk about that, okay? So, say in my neighborhood, we have a, power grid, right? I mean, we have a power, being sent from the utility station and all that. And in this neighborhood, there's, transformers everywhere, right? Well, in every transformer, there's usually a line 1, line 2, and a neutral that comes off that transformer that comes to the house. And the neutral is going to have a wire tied to ground, earth ground. That's actually earth ground. And very few cases do we ever tie to earth ground, but in this AC power system, we actually do. Earth ground is tied. And it's another term here is multi-point ground system, where we ground in a whole bunch of different spots. So we have all these transformers, and they all have a ground rod or ground stake, tied to earth ground. And they're just scattered everywhere. So it's a multi-point ground system. Well, the earth ground, it is not conducting electricity very well. We don't want it to. We don't want current traveling across ground. But it's a way, it's a place where we actually use it as kind of a type of ground plane to pull the ground, the power system down to a certain reference point, so that we don't have floating voltages. And, if voltages are floating, you don't know how high they're going to be. You might have, say, 12 volts between two terminals, but that could be floating hundreds of or even thousands of volts above ground, earth ground. And you don't want to be the person touching something and transferring that energy from some voltage to earth ground, right? That could kill you, right? It only takes 10 milliamps plus or some to actually kill you, and less milliamps than that to hurt you. But around 10 milliamps plus or minus a few milliamps is where, when you hold on to it, you can't let go. And so it doesn't take a lot of current. So you don't need a lot of really good conductive earth ground for current to be flowing. You don't need a lot of current, and you got high voltages, so you only need a little bit of current to cause damage, right? All right, so at the house, back in the old days, they'd run 2 wires in from the transformer, and you'd have your AC power. And you connect those wires to a light bulb, and you complete the circuit, and you have current flowing from one wire to the other. It's AC power. there's no plus minus. It's AC, right? It didn't even matter if one's called neutral or if they're line 1, line 2. It doesn't even matter what they're called, because they were both hot. You know, you touch either one of them and touch a ground, and it could be dangerous to you. Well, here's the other thing is, let's say a washing machine. You have electric motor. That's a moving thing, right? Moving parts wear out. Even the windings inside those motors can heat up and eventually maybe short to the stator. So you have that electric motor and it's got a short in it now, and you touch it and you complete the path to ground, and it could kill you, and it doesn't take a lot of current, like I said. So even though the earth ground is completing the path, it doesn't have to conduct a lot of current, just a little bit of current, and that's dangerous. Well, the other thing is a lot of fires would happen because these motors would heat up and burn up the insulation, cause a fire, and burn the house down. Well, they decided to add a third wire, that ground wire, that safety ground wire. Now things are safe, because anything metal like your washing machine and your dryer, imagine before when they were not tied to the same conductor. So that motor could be shorted to that washing machine, and you could touch the drying machine, and that'd even be worse. I mean, that'd be dangerous, right? Now those two things, the metal, the chassis on those things, the frames are tied to those ground wires. Okay, so all appliances, when you have the power coming in, you're going to have your neutral, your hot, and your ground, right? So the ground wire, first thing it does is it enters the appliance or any of the equipment. The first thing it does is it goes right to the metal chassis, ties to the metal chassis. Screwed, it's bonded down, another term, okay? So all those ground rods and all those transformers in the neighborhood, they're all bonded to ground wire that goes into the ground. At your house, where the power comes into the service entrance, another term, that's where the power enters your residence. There's a power meter. That's where the service entrance is, and that power meter obviously monitors the power so they know how much to charge you. But there's also a bond point there where your earth ground is tied to the neutral. It's the only place in your house that it should be tied together. So they tie it at one spot, and that's at the service entrance. All right, so then that green wire, and ground is usually a green wire, a lot of times with the yellow stripe, sometimes solid bare wire. But that wire goes to all your receptacles and ties all your equipment, anything with the metal housing, let's say. Anything with the metal housing with 3 prongs, it's going to take that third prong, that green, that ground prong, and tie that chassis to earth ground. Okay, so now what happens is if you have a short in that washing machine, that drying machine, where the motor shorts to the housing, well, that housing's tied to ground, that ground wire, which is tied to the neutral. So now the hot wire touches it. Now you have a direct short from hot to ground, which is essentially tied to neutral, back to the service entrance. So you have a lot of current racing through your circuit breaker, and it pops your circuit breaker. So that protects you. Okay, so that's protective earth ground. And also part of protective earth ground, like I say, it ties all the metal together. So anything metal, when you touch any of the metal, it's pretty much the same voltage potential, right? There's a slight difference maybe because, as current travels through the neutral wire or the ground wire, there's some voltage drop. So there could be slight changes from one piece of equipment to maybe something over here, very slight. And that's because that ground wire actually has a little bit of current flowing through it. Really, we don't want any current flowing through it unless there's a fault, so it's just 0 volts. But there actually is just a little bit of current. It's leakage current. All these things have EMI filters. Those EMI filters have X capacitors tied from hot to neutral, line to neutral, and they also have capacitors, Y capacitors, tied from line to ground and neutral to ground. So those are the Y capacitors. I did a video on those. I'll put the link down below. So you have a little bit of leakage current on the metal. It actually hopefully goes down to the green wire and just travels back that way. But that's leakage current. So if you were missing a ground wire in one of your pieces of equipment, let's say you're floating a scope. Some people float a scope, and the reason they do that is all these terminals and everything, all this metal, except for the 2-volt, calibration or compensation pin, and that's because it's real low voltage, but all this other metal is all tied to, like they show here, chassis. It's tied to chassis, which is earth ground. In other places, I see the earth ground symbol, like on the power supplies over here, the HPs. All right, so if you float the scope, these things can have a little bit of voltage on them because that leakage current can develop a voltage on that bare metal. And so if you touch this and say touch your generator or touch something else, you could get a shock, and that can be dangerous. So, that's why it's not recommended to float your scope. The reason people do is if they're looking at AC circuit where they're on the primary side of the power, which we'll talk about primary and secondary side, but if you're on the primary side, meaning where the power comes in, and you have that little ground strap tied to anything but earth ground or chassis ground, the scope probe is going to short that to, whatever you have it tied to. Say you accidentally put it on the 5-volt output, it'd short that 5 volts to chassis because over here it's tied to chassis. So some people will float their scope so that doesn't happen. And maybe it's safer for the scope, maybe not safer for the person. So it's not recommended practice, but people do that. And people do it on other kind of devices. You might have a power cord or an extension cord that doesn't have the 3 prongs. So you use one of those, what they call the cheater plugs, some people call it cheater plugs, that goes from 3 prongs to 2 so that you get rid of that ground connection and you can use an extension cord. So you just have to be aware of that those are safety risks. So as a matter of fact, the company paid me some years ago to advise them. They wanted me to write a white paper. So let's say I've got this multimeter here, and it's a plastic box, but this multimeter actually has 3 prongs. It doesn't have to because it's plastic. There's nothing that you can touch, you get shocked. So actually it could be 2 prongs. I would think that they're probably using that 3rd prong to get some extra quiet EMI filtering and some noise reduction or something. But when they asked me, this company asked me to write a white paper, they had vendors making these products. There's several different vendors making these products for them, and they're putting their name on it. And they sell them by the millions in the household. So in your living room, in your set-top boxes, say a cable box could have one of these items. And some of their vendors use power cord with 3 wires, some use 2 wires. And they asked me, what do I think? Would I write a paper? And I'm like, sure. So I'm thinking I'm going to write a paper telling them to use the 3 prongs because that makes it safe. But then I realized, well, it's a plastic box, and I think it's actually safer to use 2 in that case. And the reason why is because of that 3rd prong being defeated sometimes. If you defeat that prong, then that prong itself is going to have some voltage on it, and if there's any metal that you can access somehow, it's going to have some voltage on it. But that prong all by itself just hanging out there in the breeze, if it's not plugged into something, is going to have some voltage on it, and that's potentially dangerous. So if you got a plastic box, there's nothing to tie the earth ground to, and so you don't really need it. So I thought it was safer just not using it. So they should only have 2 prongs. So I think you'd probably see those boxes, millions of homes in the U.S. at least, would only have a power cord, 2 prongs, because of my white paper. So anyway, that was the story on that. But sometimes 2 prongs are the way to go, sometimes 3 prongs are the way to go. Anytime you have metal, it's 3 prongs. You need that ground. You need to tie that to, you want, even if there's nothing moving like a motor that could potentially touch that metal, so even if you're not concerned with that kind of thing, you still don't want any kind of leakage voltage, or you don't want 2 metal things you could touch. Okay, so That's the safety issue. And here, let me just show you the symbols, okay? So we're talking about symbols, so let's make sure we're using the right one. This symbol right here, you see lots of times in the schematics. A lot of times audio circuits, audio guys will use that everywhere. I don't think it's correct to do that. It's kind of a general purpose symbol from the old days, and it just kind of shows that they're old school guys that still using symbols that don't really tell you what the circuit's connected to, because they're not connected to earth ground. I mean, yeah, so there's parts of the circuit that are actually isolated from earth ground, but they'll show that symbol. So yeah, I don't like that. I don't think it's correct. So this is the earth ground symbol. This one they had to come up with to say, geez, guys, you're abusing that symbol. We're going to come up with the circle around it so we could say that's protective earth. So now, really, this one can be used in some equipment where you're just grounding the equipment. It could have a lot of leakage current because it's meant for industrial use or something like that. In a home or certain places where humans are, you want to limit that leakage current, and so to make it safer for humans. So that's usually where protective earth ground is used. Correct me, any of you guys out there that want to define that better. But and this one's chassis ground. So this one here is where you tie your conductor to chassis, and it shows you that, yeah, that is physically tied to chassis right there. Okay, so where you physically make a chassis connection, so you can have say a ground plane on a circuit board, and you're going to take a wire from that and tie it to chassis, so you would use that connection. Okay, and you'd show an earth ground connection, maybe outside your box, or where just showing that you've got 3 wires and there's protective earth ground. Okay, so those things there, they really should only be used where they're physically showing what's happening. They're just not meant, like this guy here, even though people use as a general purpose ground, they're really, I think they should be kept and used where they really mean something. And then where you just have a signal ground, use a proper signal ground. Okay, let me show you those. All right, signal grounds. Now, a lot of times, now obviously all these shapes, they're all identical. You can tell they're scaled perfectly. I drew them just perfect, right? Well, okay, just pretend that. But really, they're all the same symbol. The difference is it could be open, it could be solid. It could have a letter in it, like A for analog ground, D for digital ground, or just 1 ground, 2 ground, 3, 4, 5, 6 ground. Or it could be P. Now, that's not for power, that's for primary ground. S, a lot of people use that everywhere for signal ground. Really, signal ground just needs to be this guy. Doesn't need to have an S in it. Come on, guys. Power guys, we like to use P for primary ground, S for secondary ground. That means something. It means that this is on the isolated side of the transformer. This is on the power side of the transformer. Okay? Alright, guys. So anyway, so these symbols, these letters or numbers, they don't have to be inside the symbol. Sometimes the symbol is small, so it could be placed on the outside, on the bottom, up, it could be placed anywhere around the number. Okay? But if you're using, like, say, digital ground symbol in a lot of different locations, then if you put the D inside, it's going to obviously be inside on every one. But if you put it up here in every location. So one time you don't put it here, one time you don't put it here in the same schematic. Or even if you have different schematic pages, because it's just confusing if you have multiple grounds and they look different. So, yeah. Okay, let's talk a little bit more about our schematic and how we use ground symbols, okay? Okay, so basically I just want to talk about ground symbols and what they are, and let's just talk a little bit more about these kind of grounds and the difference between the chassis ground or the power, safety grounds, okay? All right, so there's what we just talked about were the types of grounds that are meant for safety. Mostly, for safety, and then for signals to show the difference between the power grounds that are really meant to keep us safe, and then the kind of the grounds we use in our circuits, our circuit grounds, our signal grounds, okay? And those are usually used for low voltages. They can be used for high voltages too, but usually they're used for safer voltages, like the category 1, category 2 type stuff. You know, our meters are pretty much any meter can read. And those other scary ones outside of category 4 or category 3, and you know, those kind of grounds are really important that you know where they are, because like I say, they're, you know, life or death kind of thing and safety. So now when we're talking about grounds in general for our circuit boards, and you know, a lot of the grounds we find, like say in this multimeter, they're isolated grounds. Like anytime you have a battery operating something, that's isolated from everything else. Obviously this, whatever's in here is isolated from everything else, right? Another one's your car, right? The car is isolated. It's got rubber tires. It's isolated from earth ground. It's not connected to anything. It's just powered by a battery and or an alternator when the car's running. Well, that battery back in the day, they used to be 6-volt batteries, and they'd put them in tractors and cars and that, and they put the plus to the chassis. So they used the chassis as a ground plane. The plus 6 volts was the ground plane. The minus side of that battery, so in this case you would have a minus 6 volts and ground. So plus 6 volts was ground, so it wasn't called plus 6 volts because it was 0 volts, it was ground. So minus 6 volts was your voltage that powered up everything, okay? And so it was just kind of like basically taking all your circuits and putting them upside down and tying your plus to your ground. It's kind of showing the ground is just a reference point. It doesn't have to be 0 volts. It can be any voltage. And whatever voltage that happens to be, if you're saying ground is 0, okay, that's my 0 reference. So when I put my black probe on ground, so in this example it's plus 6 volts. When I take this probe and I probe around, I'm going to read minus voltages, right? So it's just a reference. And that seems confusing now, since we're so used to having positive on top and ground as the lower voltage, as the 0 voltage, and positive being the voltage that we're probing around. Well, I think the reason they did that was for corrosion reasons. If you had the plus voltage on the metal, then it was, I think the electrolysis was different versus putting the negative on the chassis. So yeah, correct me if I'm wrong about that. It's kind of, you know, an interesting question, like why did they do that? And you know, we know that back when it was 6 volts and they changed it to 12 because they want to use smaller wire. Same amount of power, they could get half the current if they used, you know, double the voltage, right? So they went to 12 volts, but why did they switch it? Well, now another thing I heard about the 6 volts, the minus 6 volts, was that if you put the plus on the ground on your spark plugs, the outer shell that's tied into the middle of the engine was plus, and that little electrode in the middle was negative. And those electrons would go from that little probe off around to the spark plug, the part that's bolted in, the big circular ring, and there's less wear on the circular ring as the electrons jumped over to it. So I don't know if that's true or not, but I heard that was a benefit. And I've heard the guys that work on tractors, especially those old tractors with the negative 6 volt systems, they just don't have the rust that the plus volt, you know, the other voltage, when you flip the battery around and put the negative to the chassis, they just showed more rust. So there could be something, that corrosion story, I don't know. But another reason, so why did they switch it back? Well, from another story that I heard was that, so when they came out with the alternator, where they would convert the AC right to a DC to charge the battery and run your DC power, they came up with these new diodes. They looked like big old nuts, basically, big old bolts that you bolt in to the alternator, and so that helped heat sink them. But the case turned out to be the cathode, which was negative. So they wanted negative on the cathode. And then the electrode was positive. So it was kind of like the opposite of the story I said about the spark plug. And that's just the way the diodes were. So I don't know if that's true either. I imagine they switched over for a number of reasons, and maybe that was one of them. Who knows? Maybe that was just a benefit of switching over. But anyway, so yeah, your car's an isolated ground system, right? And it also shows how you can use a chassis, a multi-point ground system. You could just take something, tie it to the chassis. You wouldn't have to have that ground wire in your harness. You'd only have to run one wire out to, say, a radio to turn it on, right? So it's, say, weight and the size of the wire harness to use the chassis, the metal chassis, to actually run current through it, which again, not great for having the metal rust. So anyway, yeah, so that kind of shows how you can use a chassis for a ground plane. Also in RF electronics, high frequency stuff, it wants really low impedance on the ground plane, and so they use the chassis as a ground plane for RF. So that's another reason you do it, to have a really low impedance. And usually the RF products are localized. Ground planes are small, small devices, and so the ground planes are really small and the chassis are real small. You're not putting it through a big old box usually. But okay, well anyway, so ground planes, yeah, part of the reason why they would use a ground plane, which is essentially a multi-point ground system, right? You just, whatever device you have, you tie right straight to ground, and so to the chassis or whatever, so you got multi-point ground system. Where in other cases you have a single point ground. You have all your electronics on a board, everything tied to different grounds, and then each one of those grounds, say digital ground, analog ground, maybe one point in the product, you'll tie them all together. So that's a single point ground. So that's an advantage, because if you are isolating, say, digital ground and analog ground, and those circuits are operating on their own ground systems, you might not want them talking to each other and sharing currents. So you take them at one point, and that way you tie them, reference them to the same point, so they're not floating around from each other. Also, if there's a chip that's communicating from analog signals to digital signals, at that point you can use that as your single point ground tie, and then they're at the same reference point too. So yeah, there's a lot of different ways to use ground. Ground comes up in all kinds of different questions about how do I do this, how do I do that. But using the proper ground symbols is a good start. And just understanding ground symbols. Like a product like this, portable product, battery operated. It's an oscilloscope I've had for a long time from Tektronix, THS 730. This is an awesome scope. Loved this scope back in the day. Today it has kind of a small screen, I guess. This mixed sig is pretty darn nice. One advantage this guy had, he only had 2 channels, but they were isolated from each other. So galvanic isolation. So that's another term, galvanic isolation. When you isolate your grounds, like something like this, like for a power supply guy, I'm looking at, say, primary ground, where the primary power comes through, and then I take the power supply through a transformer, and I put out these secondary voltages, say 5 volts, plus minus 12, 3 volts, that kind of thing. They're all on secondary ground. They're galvanically isolated from the primary side. So there's no current that's shared between the primary power coming in from the wall and the stuff you're powering, the circuits. Galvanic isolation is when you take an ohm meter and you put it, say, from primary ground to secondary ground, you don't read any current flow. There's, lots of ohms, okay? Mega ohms, whatever. I mean, it's open circuit. So that's galvanic isolation, where there's no DC current path. So you want to depict that in your schematics. You want to use one of those ground symbols I showed earlier for your primary ground, and you want to use the other symbol for your secondary ground, so people can see on your schematic, oh, that's tied to my secondary side, that's tied to my primary side. Maybe some of those voltages I'm sending to a digital card, and they're not tied to the analog side. Maybe those cards are in different boxes, and there's different connectors and cables that go to these things, so I want to keep all that stuff separate. So analog ground would go off on itself. It's a secondary voltage, isolated, but instead of using the analog, or instead of using the S for secondary, I'd use an A for analog, or D for digital, and you would just know that those also, all those symbols I showed, those triangle symbols, would all be considered on the secondary or isolated side. Generally, okay, they should be. That's what I mean, is you got to, if we're in the habit of using the proper signals in the proper places, we just know these things. But when you have to second guess people because they use the earth ground symbol everywhere, because they just don't know any better, and they've always done it that way. Well, we've always done it that way. I mean, don't you love that reasoning? But I hear that all the time. Well, we've always done it that way. It's like, well, you always want to be wrong? Okay, continue being wrong. It's like, all right, go ahead. Arr. So, yeah, so I want to do this video, just talk about grounds, because some of it's really safety stuff, really important stuff. Everything's important, but some of it's direly important, and some of it is just, you know, the art of electronics, using the proper symbols in the proper places. So, hope you guys like this video, that it makes sense. So I'll also put a link where I show how to use a scope safely, the ground, you know, how not to blow up your scope. I think different people have done those videos. I did one, so maybe I didn't need to do another. But anyway. All right, guys. Hey, and by the way, I put these 2 meters out here. I'm going to review these meters. Dave Jones gave me this meter. Awesome of him to do that. And he did a review of a 77 and his meter. He kept saying it wasn't a review. He just kind of opened them both up just to kind of illustrate the build quality of each meter. So I'm going to do a review of this 79.3 and this guy, okay? So anyway, that's why they're hanging out there. So, all right, guys, so thanks for watching. Appreciate you watching the video. Oh, I want to give 2 thumbs up to my patrons. Really appreciate you guys. And you can become a patron for as low as $1 a month. Just got to throw that out there. And thanks for watching. We'll see you next time.